Right, what we have here is a flowchart to help you make decisions regarding what type of analyses you need to be using for your data. Now, as many of you have noticed, it's important not simply to be using a formula, make sure you're using the correct formula particular situation. So this flowchart should help you in making that assessment. I suggest you print out a copy of it and keep it for your own reference to help you use as you're going through your homeworks and especially on the exams. So if we see here, if we know what our standard deviation is for the population, then we can see that we're using primarily the z-normal distribution, which we've been focusing so far on Chapter 6. Now what we're going to be looking at here today primarily is if the standard deviation is not known, then we're going to move to the right of this flowchart and we're going to wind up working with the t-distribution, which we'll be working with in Chapter 7 and Chapter 9. So in Chapter 7, we're going to be looking at estimating a population mean and how we use that. And in Chapter 9, we're going to be looking at t-test comparison of means from two or more populations. So the student t-distribution table is on page 586 in your book. It was developed by William Gossett, who lived 1876 to 1937, and he was in charge of quality assessment at the Guedes Brewery. He developed the t-distribution table because he needed a method for assessing the quality of smaller samples. Guinness was a very small local brewery at that time and was not able to have the samples of N or larger that we tend to prefer for the Z distribution table, yet Gossett still need to be able to do probabilities of quality assessment as we've been looking at before when we were looking at doing accepted sampling. So he designed, as a mathematician, the t-distribution. He published it under the name of student because at that time Guinness did not allow their employees to publish their information as research in journals. So he published it under the pseudonym of student, and thus we have the student t-distribution table developed by William Gossett. Now, to use this t-distribution table is our alpha level. So we need to have our alpha level, which is calculated via our confidence interval. So we take our confidence interval percentage, you divide that by 100, right? And then you subtract that from 1. So here, with a 95% confidence interval, we have 1 minus 0.95, and that equals 0.05 for the alpha. The next thing we need is our degrees of freedom, which is calculated by n minus 1. And our last part is a directional, so whether it's a one-tail or a two-tail, which case it is non-directional. And I suggest you take a look at your table again, A3 on page 586, and you can see the diagrams of what these different distributions look like in terms of having a one-tail left tail or a one-tail right tail, or again the two-tail for the t-distribution table. So unless otherwise specified, you're going to assume that it's a two-tail. So if they're not telling you in the problem that it's looking for something lesser or greater than or otherwise indicating directionality, then you should use the two-tail. All right, now there's several important properties about the student t-distribution that we need to look at. So first of all, it is different for different sample sizes. As you've noticed, you have to use your degrees of freedom to locate the proper probability in the t-distribution table because the shape of the distribution changes for each different sample size. Notice we didn't have this information, we were using the z-distribution table. That was standardized for all sample sizes that were meeting the requirements for using the z-distribution table. Now, here we have the t-distribution has the same bell-shaped curve as the normal distribution shape, but it is wider distributions with smaller sample sizes. This means we have greater variability. All right, so here we can see with our distribution for n equals 3, which is the yellow line, is wider than the one for n equals 12, which is the red line, showing the increase in the variability. Our mean for the t-distribution is going to be equal to 0. However, our standard deviation is going to vary by sample size and is always greater than 1. This is an important difference because in our standard normal distribution, keep in mind, of course, our standard deviation was equal to 1. Now, as the sample size gets larger, it gets closer to the standard normal distribution. So here you can see if you compare the shape for the yellow line for n equals 3, you can see that it is further away from the blue line of the standard normal distribution than the red line for the n equals 12. So you can see the yellow line is both wider and also less peaked at the mean. This is because of our central limit theorem. So as we looked at with the applets, as your sample size increases, the distribution gets closer to the normal distribution shape.